Okay, we're going to have a look at the oxidation reactions of alcohols and the alcohols topic of AS chemistry. So we'll skip through this and have a look at sort of the oxidizing agent, the colour changes, have a look at some reactions that you need to be able to write and the practical implications as to what particular type of oxidation we want to go with. Okay, So if we look first of all, the oxidant or the oxidizing agent is acidified potassium dichromate. That can be acidified sodium dichromate also in aqueous solution. It actually dissolves in dilute sulfuric acid. So when you're asked for the oxidizing agent, you must include that it's the potassium or sodium dichromate in dilute sulfuric acid. Okay, you can't leave out the acid part. The equation for what's happening in here, the half equation for what's happening to the dichromate, is as so the dichromate Cr2O72 minus ion. Note the potassium isn't in here, this is the ionic equation, so it's only a spectator ion, is turned to a chromium 3 plus ion. We get 7 waters there. Now why does that allow us to follow whether an alcohol has or has not been oxidized? Well, we conveniently get a colour change here. So if potassium dichromate is able to oxidize the alcohol, and it will itself be reduced, and in doing so it goes from chromium in its plus 6 oxidation state to chromium in its plus 3 oxidation state, hence reduction in oxidation number here, plus 6 to plus 3, and that is accompanied by an orange to green colour change. So dichromate ions in solution are orange, chromium 3 plus ions in solution are green. So we can tell if the substance has actually been oxidized or not by that visible colour change. Now, you have 3 different types of alcohol that we studied at the start of this topic. You have primary alcohols, which will undergo oxidation, and when we're writing equations for oxidizing agents, we don't have to put all of this dichromate ion, etc. in at AS level. We can just represent the oxidizing agent by an O in square brackets, and we'll look more detail on that when we're writing some equations. We can oxidize that in 2 steps of primary alcohol. Firstly, it will go to an aldehyde, and if we continue to oxidize through mild oxidation, or partial oxidation, if we continue to oxidize that to complete or full oxidation, we will get a carboxylic acid. Secondary alcohols will be oxidized to a ketone. They don't go oxidize any further. Once they get to that, that's it. And tertiary alcohols will be oxidized not at all under these conditions. They can be oxidized, but not under the conditions on the AS chemistry course. So we'll have a look at how we would practically try and get a primary alcohol just to go to an aldehyde and not go to a carboxylic acid. And then alternatively, if we wanted to get the carboxylic acid or the ketone, what would we do in that instance? So that will be determined by the type, the practical apparatus that we choose, whether that be distillation at the top of the screen or heating under reflux at the bottom of the screen. So if we think of this, if we put our oxidizing agent and some of our alcohol in here, okay, so we're trying to get in this top apparatus will allow us to go to the aldehyde and prevent further oxidation to the carboxylic acid. And what happens is you put your aldehyde and your oxidizing agent in there, and you make sure your aldehyde is in excess, or you can also put a little sidearm on here, and you can add your oxidizing agent nice and slowly. Okay, but what you want to avoid is lots and lots of oxidizing agent in here, because what that will do is it will turn the primary alcohol to an aldehyde and then encourage the aldehyde to go further to a carboxylic acid. So we do that, and then as soon as the aldehyde is made, this is distillation, so the more volatile substance in here with the lower boiling point, which is the aldehyde, because that only has dipole-dipole attractions, whereas the alcohol will have a stronger hydrogen bonding and have a higher boiling point. So the aldehyde will therefore up and across and can be collected at the other end, and that separates the aldehyde out to a purer form of the aldehyde. Now there's other purification steps that need to be taken to get a very pure form of it. So that's distillation, and that would give us a relatively pure aldehyde. And we would keep adding a bit from our sidearm if we had one, a little bit of the oxidizing agent at a time, and keep just oxidizing the primary alcohol nice and slowly. However, if we wanted to push this right through to full carboxylic acid, full oxidation, or the secondary to get as much ketone as possible, this time we would use heat under reflux. And that means that everything that's in the flask here gets heated and boiled and remains heated and boiled. The vapors will rise up the inside of the condenser. They'll hit the cold surface of the condenser, and they will return back to the flask, to the pear-shaped flask. And we get this continual evaporation and condensation of the reactants that are in here. Okay, and that means that we are able to reach very high temperatures for a very long time, and that's important because these things have strong bonds and we've got high activation energies. It also means we can heat these things for a long time without losing any reactant or product, because they're very volatile. If I did this in a beaker, for example, with heat, like we might have done for some things at GCSE, the volatile reactants and products could simply evaporate off into the room and we'd have nothing left at the end. Okay, so that's how our reflux happens. We would, in this case, use an excess of the oxidizing agent, so lots of it, to make sure we push this process right through to the end and get as much product as we can. And then when we were finished with that, we would rearrange the reflux apparatus. Okay, reflux apparatus, we would rearrange that to distillation apparatus up here, and we would distill across and collect. So let's say we were collecting an aldehyde, or making a ketone in here which had a boiling point of 120 degrees, let's say. We would distill across and collect our product here, probably between about 119 and 121 degrees Celsius roughly, and we could be pretty confident that that was mostly the desired ketone product that we were getting. We would use further steps to remove maybe any acid or any water that's in there. Okay, right, so that's how we get what we're after. That's the chemistry behind it. We'll look now at just a few little equations that you would maybe have to write for the oxidation of we'll take a primary alcohol first. We'll take one with two functional groups on it. Okay, so this is a primary, this is a diol, propane 1,3-diol. Okay, and we're going to oxidize that. Now, we've got two functional groups, but they're both primary functional groups, so they react in exactly the same way. So the first one that will happen is when we oxidize it with our oxidizing agent, we'll turn it, because it's primary, it goes to an aldehyde, and you need to know that aldehyde functional groups are as so. Okay, hydrogen there and hydrogen there. Okay, and along with that we will get two water molecules, and we will need to balance that out with two O's and square brackets there. If it was just one, well then we would just have one group here. This would be a CH3. We would only have one O in square brackets and one water. Okay, and that is a new product, and that is called ethane. No, it's not. That is called 3 carbons, propane 1, 3, although they're probably strictly not needed, the numbers, because if there are aldehyde groups they have to be at the end. Okay, and they are aldehydes and they end with al, but because there's two of them it's a di-al. So if it was just one on its own, it would be propan-al. There would be no E there. E only comes in when we have a dial. Okay, if we then further oxidize that, okay, excuse me, to the carboxylic acid. Okay, so a carboxylic acid functional group is as so. So we just take the functional group of the aldehyde and we turn it into a carboxylic acid. Okay, so this is now my carboxylic acid. Again, I need two of those, sorry. There is no water produced this time, so please be careful of that. And then we have got ethanol dioic acid. Oh, what am I doing? 3 carbons, apologies. We have propane dioic acid. Again, we don't need the numbers, probably don't need them up here, because when you have a carboxylic acid group, like an aldehyde group, they can only be on the terminal carbons, they can only be on the end carbons. Okay, now, you might get asked, why is this one here oxidation? Why is this treated as oxidation? And some people might talk about loss of electrons, some people might talk about gain of oxygen. Well, there's two oxygens here and there's two oxygens here. It's actually because of the removal of hydrogen that is defined as oxidation. Okay, this one down here is because of the addition of oxygen, that is oxidation. So you have oxidation going on here and here, but for two different reasons. Okay, now, so all you got to do is remember wherever your functional group is on your original, provided you know what an aldehyde functional group is, you just take the original functional group, the carbon on it, and you turn that carbon into the new functional group. Likewise down here, provided you know what a carboxylic acid functional group is. Okay, you do that. Okay, now, I think if you can do those, you should be fine. Alright, and then each time, just as I sort of said, whatever the other part of the molecule is, you just redraw it, redraw it, redraw it. It doesn't change from one molecule to the other because it's not involved in the chemical reaction. Okay, hope that makes sense. That's primary done. Okay, we look at how secondary alcohols then react. So remember, secondary alcohols are alcohols which have an OH group on a carbon which is attached to two other carbons. Okay, so we'll take this is propan 2-ol here, and we'll oxidize that. So again, we just write O in square brackets, and we convert that. So our functional grouped carbon is that one. Okay, which is this one here, and we convert that to a ketone, and a ketone functional group is as so. So this hydrogen disappears, frequently get that drawn in, and that would leave carbon here with 5 bonds on it, which wouldn't be right, plus H2O. So this is a ketone, and this is prop, pan, on. There's no number needed because a ketone group can never be on the end, and if it's prop, it can only be on the middle. Okay, if I changed it to this compound here, so butan 2-ol, I would do that. I still don't, so I would change my compound, sorry, is butanone. I still don't need a number because if it's butanone, it can only be here or here, and either way it's going to be 1, 2, 1, 2, so it's going to be 2. So it would only be once I get into pents. Okay, so 5 carbons in the chain. The functional group could be here, or it could be here, or it could be here. If it's here or here, it's going to be pentan 2-on, but if it was here, it could be pentan 1, 2, 3-on. So in this case, it's pentan hyphen comma hyphen 2 hyphen pentan 2-on. Okay. Let's say they made it a little bit nastier for you and they give you something with a primary group here and then your secondary group here. We just treat them completely independently. So in the first oxidation, okay, you will get the secondary going to a ketone, and you would get the primary, as we had on the last slide, going to aldehyde. Okay, and then if you did further oxidation on it, the ketone, if you remember, does not undergo further oxidation, whereas the aldehyde, as per the last slide, turns to that. Okay, so no water in this one here. We just need one oxygen this time because we've only one functional group getting oxidized. Okay, this would be named, it's a 1, 2, so it's a pentanal. Okay, the higher priority is the al group. This ketone group When it's the second or lower priority group, becomes an oxo. So it's number 1, 2, 3, 4. We always lumber from the high priority functional group. So that'll be 4 oxopentanal. No number needed. The al group is always assumed to be on the end. Here we would have again pentanoic acid. Carboxylic acids are the highest priority group of the lot. So it's pentanoic acid. Again, no number needed because it's always at the end of assumed position 1. And again, it would be 4 oxopentanoic acid because the ketone group is lower priority than the carboxylic acid group. Okay, that was a quick roundup of those reactions and sort of the equations. So you just need to be able to apply those to the question that the examiner gives you. The structure will probably be different than the ones I use, but the principle behind working out the structure of the product and the name of the product and writing the equations and balancing them should be fundamentally the same.